for today's lesson, what I want to do is talk specifically about how bonds work in chemicals. I guess first reminder, what are chemical bonds made out of? Kind of. Positive charges are found in nucleuses, though. Good. Bonds are made from electrons. Right? If you're, I'm doing this with my grade 11s right now. There's two types of bonds that we mostly talk about. There's ionic bonds and covalent bonds. Ionic bonds are what? Transfer of electrons. So the electrons are basically the make up the bond, right? Whereas covalent bonds, they share electrons. So long story short, you've got electrons making bonds. Does that make sense? You guys remember this? If you want to break a bond, it's going to take some energy. I hope that kind of makes logical sense. There are bonds in this chair right now. The chair is not just randomly falling apart and I land on my butt. Does that make sense? Because it's going to take a lot of energy to make those bonds break. If I were to throw this chair into a furnace, like a big, fiery, something like that, could I eventually melt this chair down? Sure. I could break those bonds. But does it make sense intuitively that it's going to take energy to break a bond? So then the opposite applies when you make a bond. When you make a new bond, it actually gives back energy. So I have like some definitions up here. When two entities move apart, it takes energy to break them apart. Otherwise, stuff would just randomly fall apart all around us, you know? That makes sense? Stuff would just start decomposing right in front of you. Whereas if you want to make a new bond, it actually gives you energy. Which that one, in my mind, I don't remember that one quite as well. Because it doesn't make sense for me that if I make a bond, that it releases energy. But at the very least, I can think that if I want to break a bond, it's going to require energy. So then the opposite should happen if I want to make a bond. Does that make sense?
Is that universally true? Like,
Yeah.
there's no bonds that...
As far as I know. As far as I know. It takes energy to make a bond fall apart. Therefore, it's going to require energy to put it back together. So, what I want to focus on then is... that's a slide there. I want to focus on how this works in terms of reaction types. Hey,
We're good.
we good?
Yeah,
When can we get it?
I got it for tomorrow, so we can pick it up tomorrow.
Cool, thanks,
Just
Larry.
need to make sure we have a big enough vehicle.
Okay,
Because they
so
said it was
we need a truck then?
fairly large, yeah.
Okay.
And they didn't have instructions for it, or
Do they have the mix for it?
no.
Okay, so we need to buy some cotton candy mix then.
Yeah.
Okay, I'll look into that.
Okay.
Do you know anyone with a truck that can help move it?
I can.
You can get a hold of it?
Yeah.
Okay, cool. Thanks, Larry.
Yeah.
Sorry, guys.
That kind of sounds like Breaking Bad.
We're making cotton candy for Pink Shirt Day.
For what?
Pink Shirt Day is on Wednesday,
Oh,
so
Pink
student
Shirt-
council's
this
making
Wednesday?
cotton candy.
Yeah, that's Wednesday.
This Wednesday.
Well, thanks for telling us.
Now you know.
It's
It's up there.
yeah, I can't read that with my contact lenses. They're too small.
Okay. Imagine that you're trying to... I don't even care what the reaction is, but just to envision something in your mind, why don't we consider blowing up dynamite? So imagine you've got dynamite that you want to blow up. As you break apart the bonds in the actual dynamite, does dynamite randomly just blow up, hopefully? No, you need to actually get dynamite going for it to blow up, right? And so you have to input a little bit of energy to actually make the bonds inside the dynamite blow up. That make sense? How do we do that in terms of dynamite? What do you do to make the dynamite get started? You light a fuse, right? So if you input some energy and you up the energy, you can actually cause the dynamite bonds to break apart. Now, do those bonds just remain apart? No, like when dynamite blows up, imagine dynamite is like made of hydrogens and carbons and oxygens. Does it turn into just purely hydrogen gas, purely oxygen gas and carbon, or what are the products of a combustion? CO2 and water, right? So you break apart the bonds. Can bonds just remain apart the whole time? I would say no, you have to reform something new, right? And so you're reforming CO2 and water. Except see, you always have to have both halves. You can't just break bonds and just leave them there. Otherwise, what you'd have is just a pile of atoms just sitting, laying on the floor. That makes sense? I have a visual. No, I have them here. Give me a sec. I ever do molecular model kits with you guys last year? Stuff like this. So, yeah. imagine that these are some compounds here, right? Okay. These compounds, they come into contact with each other and they want to react. Okay. So if they're going to react, all of these bonds right here are going to break. And what are these bonds again? Electrons, yeah. So the electrons are going to rearrange themselves. I have now broken all of these bonds, and I just have a bunch of atoms just sitting there, right? Individual carbon, individual nitrogen, individual oxygen. Does that make sense? Okay, so it takes some energy. I had to actually rip those bonds apart. So it takes some energy, kind of like lighting a fuse on dynamite. With me so far? Well, after I'm done, does it just sit there like that? Well, no, it has to reform new products. And so then it remakes carbon dioxide, and it remakes what? Does that make sense? Well, the process of me remaking the bonds releases energy. Depending on whether it's exothermic or endothermic, that depends on how much energy it takes to break the bonds versus how much energy it takes when you remake the bonds. Very wordy section here. If it takes a little bit of energy to break bonds, and then when you remake the bonds, you get back a lot of energy. That's exothermic. Does that make sense? If you light a little fuse, it takes a little bit of energy to get the reaction started, and then afterwards, it gives you back a ton of energy because the remaking of the bonds in dynamite is very exothermic. Does that make sense? Whereas there are some reactions that are endothermic, which will be the top one here. It takes a lot of energy to break bonds, and then when you remake new products, it comes back down again a little bit, but ultimately, like, it still costs you a lot of energy to get going. Does that make sense? I want to show you guys some graphs. Here's an example of what's actually happening in an exothermic reaction. Imagine that you've got hydrogen gas and chlorine gas, okay, and we're going to react them together. Okay. So there's a bond right here, there's a bond right here. If I want to break that bond, they don't just randomly break, right? Like hydrogen gas doesn't just randomly all of a sudden fall apart. Does that make sense? So if I want to break these bonds, it's going to take some energy. So that means I need to input some energy to get the bonds to break. Make sense? Now, all I've got sitting here are a bunch of random molecules that there's no bonds attached to them at all. Well, when these guys rearrange themselves and have like this hydrogen and this chlorine and this one bond together, and I remake new bonds, if the amount of energy I needed to get going is less than the amount that I get back, it's exothermic. Does this make sense? I feel like I'm going to say the same thing a lot today. So let me know if give me some nodding of heads or somewhere. Yeah. Okay. So I like the example of dynamite. Dynamite needs a little bit of energy to break the bonds in dynamite. And then dynamite releases a lot of energy when it remakes the bonds afterwards. And so dynamite is very exothermic because it just takes a spark just to get it going, and it releases a bunch. Do you have a picture of another one here? Endo's just the opposite. Let me draw a picture of an endothermic reaction. So you have some stuff. I don't know what that is. Let's just go with H2 and N2. And then it takes some energy to break those bonds apart. So you get H and N and N. And let's say that when H's and N's then react, and it wouldn't work this way, but let's say they went like this, and you got HN and HN. Okay. If the energy it takes to break the bonds is more than the energy you get back when you remake new bonds, and then it must be endothermic. Does that make sense? So to physically break a bond, it's going to take some energy. Why? Well, hopefully this makes sense. Otherwise, stuff would just randomly start falling apart all around us because bonds would just break, you know? What used to be a really nice, strong structure, if this bond right here could just break all of a sudden, then things would just disintegrate. It would be like a comic book villain that has like a gun that you shoot it at somebody and they all of a sudden just disintegrate. Does that make sense? That's not how our world works. Right? It's going to take some energy to break these electron bonds apart. And then you don't just leave them sitting there as just individual atoms, so then they react and they go with someone else. So then this one, I don't think this one as easily as the other one, but when I remake a bond, that released energy. Does that make sense? Okay. There are some reactions that actually occur spontaneously at room temperature. How do I describe this? At room temperature right now, is there energy in the air around us? Sure. 25 degrees Celsius, there's a little bit of energy. If a reaction only needs a little bit of energy to kind of get going, like just the slightest spark, we say they happen spontaneously. Okay. I can't think of a good one off the top of my head right now, but like a match though might require just a little bit more energy to get propane going, and once I get propane lit, then I get back a whole bunch more energy than I started with. Okay. We could call it initiation energy. The idea basically being a spark, something to get the reaction going so that it can actually happen. I'm going to jump ahead here actually. I want to use this diagram here. Let's find this slide. There's a really great analogy for how this works. It's kind of like a physics kind of example. Imagine that there's like a hill right here. Okay. And you need to roll the ball up the hill. Okay. If I roll the ball up the hill, it's going to take some energy for me to get the ball to the top of the hill. That makes sense? But let's say once the ball is at the top of the hill, I want it to start rolling down the hill. The ball's going to be going pretty fast at the bottom here. Does that make sense? Because the hill is quite steep afterwards. So is this an endothermic or exothermic reaction? I'd say it's exothermic. I have to put in a little bit of energy to get the ball up to the top of the hill, right? But once it's at the top, now I'm going to get back a bunch more. The opposite of this would be to have a really big hill and then kind of a little bit on that backside. So it's going to take a lot of work for me to get this ball all the way up this steep hill. And then as a payoff, I then roll it down the hill, and I feel kind of gypped because I only got back a little bit. Right? And so in this reaction here, it's really it's a loss. It's a net loss. This would be endothermic, whereas this one would be exo. Does that make sense? So we have a term for this. You're probably going to get tested on this on your diploma as like a theory question. They call it activation energy. It could be known as an initiation energy. You could call it a spark. But every reaction has like a threshold that you need in order for reactions to get started. Because you need to have some sort of energy for bonds to break. Otherwise, bonds would just randomly break all the time. Part of it has to do with like when these molecules hit each other. This molecule and this molecule will actually have to like come into contact and crash into each other with a collision. And so what sort of energy will they have as they crash into each other? Kinetic, yeah. They'll have some sort of kinetic energy in the form of like motion, right? Like it could be heat. It could be that they're actually moving towards each other, but they have to crash into each other. And the act of them crashing into each other causes their bonds to fall apart and then rearrange themselves, basically. Thank you. There's another term I need you guys to know. It's called activated complex. How do I describe activated complex? Thanks, Sam. You have molecules here and here, and they crash into each other. I almost think of like a collision of like a school bus and a truck or something like that. So here's the truck, here's the school bus, and they crash into each other. For a split second in time, really, they're all one big blob together object. Does that make sense? And then afterwards, they're going to separate. And so maybe the one bus happens to take the front half of the car with it or something like that, right? And it rearranges itself a little bit. That's kind of what's happening here is molecule 1, molecule 2 crash into each other, split second in time, everybody is all together. And then afterwards, they separate. And so rather than it being this guy and this guy, it looks like it separates so that this guy and this guy pull apart instead. That makes sense? So that brief moment in time is called an activated complex. And we usually represent the activated complex, I'm going to call it AC, at the very, very top up here. Or if you draw a diagram like this, it'd be right up here. We call this thing the activated complex. I wish I would have taken this course in university, but I never needed it for my major. It was called Chemical Kinetics. And it was a course all about talking about like that magical millisecond when molecule A and molecule B are in contact with are touching each other, and somehow all the bonds break, and then they rearrange themselves and new stuff comes out. I like analogies. Do you guys know what a Chinese fire drill is? What's a Chinese fire drill?
You stop at a red light and everyone gets out and runs around the vehicle.
Sure, and you get back in a different spot, probably, right? Maybe? Okay. I think of it as you do that, but like you get back in a different spot, right? So beforehand, everyone's driving in a car. Those are your reactants. Then you stop. Now you're at your activated complex. Everybody gets out of the car and runs around, right? And then you get into a new location. So the person in the back seat's now driving. The person driving is now in the passenger seat, right? And that's the rearranging of molecules, where you used to have something here, then everybody rearranges themselves, and then afterwards you have new stuff. Does that make sense? Okay. This is a very much theory kind of lesson, so I'm sorry if I'm like repeating myself. So what I need for you guys to know is from now on, we're not going to draw diagrams like this anymore. Normally I'd have you draw them like this or like this. That's really not true. They usually happen along more of a smooth curve where it goes up a little bit and then comes back down. This would be an exothermic reaction. It takes a little bit of energy to get the reaction going, so we call that activation energy, but then afterwards it releases a lot more. And then from here to here is the actual enthalpy change. That makes sense? Here's one that is endothermic. It takes a lot of energy to get this reaction going. And then on the way back down, you get back some of it, but you don't get back all. Another analogy I like to use is in terms of like business. This might be like your startup costs. It takes $1,000 to get your business running. And then afterwards, in the tills, you make back $800. That makes sense? So like $1,000 to get going. So startup. And then here you make back 800. Did you actually make money as a business? Were you profitable? No, you lost $200. You actually ended up inputting 200 more than you got back. Whereas like on a example like this is me putting in $100 to get going, right? And then afterwards I made back 1,000. So then what's my delta H? It'd be 900 in that example. Does that analogy make sense? I hope this is making sense here. I threw a diagram on here of a couple of famous exothermic reactions. The second one's the one I mostly want to talk about. Do you guys know what the Hindenburg was? Yeah, they put hydrogen, I believe, in it. Hydrogen gas? I think it was hydrogen gas. Helium would also work. Helium would be smarter because helium is not combustible, but hydrogen blows up. And all it took was a small spark to get the hydrogen going. And then once it got going, it kind of worked like this. It took a little bit of energy to get it to start blowing up. And then afterwards, it released a lot of energy. And so it was massive, massive explosion for this one blimp, basically. So we don't use hydrogen for gases like that anymore. What else should we talk about? Basically, here's the nuts and bolts of what I need you to know. They're probably going to test you with some sort of graph, picture type question, and you just need to know the different like locations on the graph. So right here you have reactants, what you start with. Right here you have products. The difference from here to here is the spark, or the initiation, or the term we use is activation energy, the amount you need to get going. But from here to here is the actual delta H. So all we care about is from start to finish. So even if you put in $1,000, but you get back 900, all I really care about is the 100 difference right here. And then the activated complex is another term you should know. It's like the topmost point, where all of the bonds are broken. This point right here is like a millisecond in time. Like for just a brief moment, there are no bonds. Or if you like the car analogy, for a brief moment, everybody has their seatbelts off and is running around outside the car. But then you're going to get back in the car and rebuckle your seatbelts up. That make sense? So it takes energy to unbuckle your seatbelts. Everybody runs around the car, finds a new spot, and then you get back energy once you put your seatbelt back on. More pictures. That's it. Does that make sense? Very much a theory-based section. Like there's not any calculations. There's no math to it. It's just you understand, I guess. So. Did I do an okay job of explaining it? Okay. I feel like I was really redundant, so I said the same thing like